Hello students, in this video I am going to solve the previous year's AHSEC final examination question from 2020 to 2025 of dual nature of matter and radiation, class 12 physics. Okay, so before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. So now let's start. So this question was asked in AHSEC final 2025. Okay, so let me answer this question. So here you see V naught is equal to H divided by nu is the frequency, minus this divided by E. Now you know the Einstein's photoelectric equation, that is half mv max, that means maximum kinetic energy, is equal to your h nu minus the work function phi naught, right? We know that this is the energy of incident photon and this is the work function of the material. There is a material, suppose, and incident photon, energy of incident photon is h nu. Then one part of this energy used up to eject the electron, just to eject the electron from the surface of a metal, and that amount of energy is called, that minimum amount of energy is called work function phi naught, and the remaining energy converted into kinetic energy of that ejected particle or ejected electron, right? So that's why kinetic energy, or you can say this energy of the photon, that must be equal to the maximum kinetic energy plus this phi naught. So therefore maximum kinetic energy, which is given by half mv max square, is equal to h nu minus phi naught, right? And we know that this maximum kinetic energy is also equal to this maximum half mv max square. This is equal to E into V naught, where V is the stopping potential. Okay, suppose this is an electron with maximum kinetic energy, that is half mv max square, and potential difference between these two plates is suppose V naught, for which this particle with maximum, this electron with maximum kinetic energy just not reach this plate. Okay, it approaches to this plate, negative plate, but it just not reach this plate. Okay, hope you have understood this. So that's why this kinetic energy, when the electron is at this position, the kinetic energy of this electron is this much, and that kinetic energy becomes zero when it reaches to this negative plate. Okay, it just not reach this plate. Okay, it's very close to this plate. So that means, that's why that amount of kinetic energy will be equal to the work done. Okay, will be to the work done to carry this electron of charge E from this plate to that plate, that is given by charge into potential difference E V naught, right? So that's why this maximum kinetic energy will be replaced by that can be replaced by E V naught, right? E V naught. So that's why V naught will be equal to H by E nu minus phi naught by E. That's why. So here we need to fill up this should be U, and here we should put phi naught. Okay, E and phi naught, that is the answer, right? So now let me take the next question. So here is the next question. This question was also asked in AHSEC final examination 2025, okay, under Assam Higher Secondary Education Council. Okay, so what is stopping potential? We need to answer that stopping potential. Okay, first let me write that definition of stopping. So here is the definition of stopping potential. Stopping potential is the retarding potential difference which reduces the photoelectric current to 0. That means, okay, now let me explain what is actually stopping potential is. Suppose if this is the photosensitive plate and this is the another plate, and light is allowed to fall on it, and electron ejected will be traveling towards the other plate. If we keep this plate at positive potential, at negative potential, so if we keep this first plate at negative potential and if we keep it in positive potential, then these electrons ejected from here will be accelerated. Those electrons will be accelerated and they will gain kinetic energy. If the energy of incident photon is more than the work function, the remaining energy will provide the kinetic energy, okay, and those will be accelerated due to the electric field between these two electrodes. Now you see, if you change the polarities, now you will make it negative and make this one positive. Okay, let's make it negative. This one is negative. Then it will repel this electron. It will repel these electrons. Okay, now if you increase this negative potential, let me say V naught, okay, it is increased to a certain value V naught, so that the electron with the maximum kinetic energy, it reaches the plate, but it doesn't touch this plate. Okay, now almost reach the plate, but it doesn't strike the collecting plate, and the photoelectric current becomes 0, and that certain value of this retarding potential is the stopping potential, right? Hope you have understood this. So here another question is asked here in the same question: is stopping potential V naught a definite value of retarding potential? Yes, it is a definite value of retarding potential for a definite frequency. Yes, for a definite frequency of incident radiation, but of different intensities. That means here you see, suppose we have a photosensitive plate here. So we have allowed a light to fall on this plate of frequency nu, intensity I1 suppose. Then whatever be the stopping potential, that stopping potential will be same if we allow another light to fall on it of different frequency, of same frequency but different intensities. Okay, it doesn't depend on intensity, this stopping potential, if the frequency is same. So we can say that stopping potential V naught is a definite value of retarding potential. It is nothing but retarding potential for a definite frequency. Okay, so next, whether this V naught is different for different values of frequencies. Yes, it is different for different values of frequencies of incident radiation, but same of same intensities. So as I have already told you that it doesn't depend on intensity, this V naught doesn't depend on intensity. Okay, if the frequencies are same, then this V naught will remain same, but it will be different for different frequencies of incident radiation. Okay, so how does the saturation photoelectric current for different frequencies remain same? So now you see here, so saturation current will be remain same for different frequencies if the intensity is same. If the intensity is not same, then the saturation current will be different. Okay, so here this condition is not mentioned that intensity is same or not. So that's why, so here we need to write no. For the first two we have to write yes. For first one and second one we need to write yes, and for the third one we need to write no, and for the fourth one, define threshold frequency. Let me write the threshold frequency. The threshold frequency means the minimum frequency of the incident light. Okay, suppose we have allowed a light to fall on a photosensitive plate, and if the energy of that light just enough to eject the electron, it doesn't provide kinetic energy. If it doesn't provide kinetic energy, it just eject the electron. In that case, the frequency of that incident light will be called threshold frequency. Hope you have understood. Now let me write the definition. So here is the definition of threshold frequency of incident radiation is the frequency below which no photoelectrons are emitted from the metal surface. Okay, that is the definition of threshold frequency. Hope you have understood this. Now let me take the next question. This was also asked in 2025. Work function is given of cesium metal is this. This is the work function phi naught is given, that is 2.14 electron volt, and the frequency of incident light is given, okay, that is 6 into 10 to the power 14 hertz. So frequency of the incident light is 6 into 10 to the power 14 hertz. And what we have, we need to find the maximum kinetic energy. We need to find the maximum kinetic energy. Okay, this is maximum kinetic energy. We need to find this, and stopping potential. And we need to find the stopping potential V naught. Okay, we need to find the stopping potential as well. So we know that according to Einstein's photoelectric equation, that maximum kinetic energy is equal to h nu minus phi naught, and the value of this h, Planck's constant, is 6.63 into 10 to the power minus 34 joule second, and the frequency here it is 6 into 10 to the power 14 hertz, and here we have work function is 2.14 electron volt. Let me convert into joule. Let me convert this one into joule. So how to convert this? Just multiply 1.6 into 10 to the power minus 19. Now it becomes joule, right? Hope you have understood this. So now minus what we have, 2.14 into 10 to the power into 1.6 into 1.6 into 10 to the power minus 19. That must joule is the kinetic energy, right? So now it becomes 39.78 into 10 to the power minus 20, and let me multiply this to what we're gonna have, 3.424 into 10 to the power minus 19. Okay, so let me do one thing. Let me write this decimal here. Okay, just give me a second. 3.9. okay, then it will be minus 19. Okay, joule. Now let me subtract. Then what we're gonna have, we're gonna have 4, 5, then again 0.554 into 10 to the power minus 19 joule. So it can be written as 5.54 into 10 to the power minus 20 joule. Okay, that is the maximum kinetic energy. Now let me find the stopping potential. So we know that just to give me a second, let me have another spot. We know one more thing, that this maximum kinetic energy is equal to E into V naught. We know that, right? So therefore V naught is the stopping potential is equal to kinetic energy, maximum kinetic energy divided by E. Okay, so that's gonna be 5.54 into 10 to the power minus 20 divided by 1.6 into 10 to the power minus 19, so that's going to be volt, right? That's going to be volt. And if we calculate this, then it should give us 3.46, approximately 3.46 into 10 to the power minus 1. That means we can say that 0.346 volt. 0.346 volt. That is the answer. 0.346 volt. Right. So maximum kinetic energy we have got 5.54 into 10 to the power minus 20 joule, and stopping potential we have got 0.346 volt, right? So that is the answer. Let me take the next question. So here is the next question. This was also asked in 2025. Okay, sorry, not 2025, it's supposed to be 2024. Okay, AHSEC final examination under Assam Higher Secondary Education Council. Okay, so for a given frequency of incident radiation that's independent of intensity. Okay, so stopping potential is independent of independent of intensity. Stopping potential okay. So now let me take the next question. A photon has a wavelength is 1.00 nanometer. That means you can say 1 into 10 to the power minus 9 meter, right? So we need to find the momentum. So we know that according to de-Broglie hypothesis, lambda is equal to h by Planck's constant by momentum, and here the lambda is given 1.00 nanometer. That means 1 into 10 to the power minus 9 nanometer meter. So here the momentum P, that must be equal to h by lambda. So h is 6.63 into 10 to the power minus 34 divided by lambda is 1 by 10 to the power minus 9, means you can write simply 10 to the power minus 9. So here it is momentum, so kg meter per second, right? So that's gonna be equal to 6.63 into 10 to the power minus 34 plus 9, that's gonna be minus 25, right? Kg meter per second. That is the momentum, and we need to find its energy. Okay, we need to find its energy. How to find the energy? So in terms of energy of a photon, h nu is equal to, in terms of lambda, you can write c by lambda, hc by lambda. So again h is here 6.63 into 10 to the power minus 34, and c is speed of light, 3 into 10 to the power 8 divided by lambda 10 to the power minus 9 here. So again what we're gonna have, just let me do one thing. Okay, let me write these things here. Okay, this is the momentum we have got. Now let me find the energy. This is number 2, answer to number 2, this is the answer to number 1, right? So joule, so that's gonna be, let's multiply these two first. 9, 18, 1 carry, here it's gonna be 19, so 19.89, right? Okay, 10 to the power, so minus 34 plus 8 plus 9, right? So that's gonna be 8 plus 9, that's gonna be 17. So minus 34 plus 17, that's gonna be minus 17 joule. So this is the energy, okay, of that photon, right? Hope you have understood this. And if you want to write this answer in standard form, then you can write it this way. 1.989 into 10 to the power minus 16 joule, right? Hope you have understood this. So here momentum we have got momentum is equal to 6.63 into 10 to the power minus 25 kg meter per second, and we have got energy is equal to 1.989 into 10 to the power minus 16 joule. That's what we have got. Now let me take the next question. So this was also asked in AHS 2024. The threshold frequency is given for a certain material is this. Okay, threshold frequency nu naught, that is 3.3 into 10 to the power 14 hertz, that is given, right? Okay, and if the light of frequency is 8.2 into 10 to the power 14 hertz, then calculate the cutoff voltage. Now you see, so if this is the threshold frequency, then we will get the work function H into threshold frequency. That's gonna give us the work function, and we're gonna get the energy of the photon H nu if we multiply Planck's constant with this, right? Energy of that photon. And in order to find the cutoff voltage, we know that maximum kinetic energy is equal to H nu minus phi naught, and this maximum kinetic energy is equal to E into V naught. V naught is the stopping potential. So let us find V naught is equal to H nu by E minus phi naught by E. Now let me put the values here. Then what we're gonna have, then V naught will be equal to H nu is here, instead of phi naught we're gonna write H into nu naught. Okay, H into nu naught. So okay, let me take common H by E and nu minus nu naught. Okay, so then what we're gonna have, let me write here. So V naught is equal to H is 6.63, let me write it clearly, 6.63 into 10 to the power minus 34 divided by E is 1.6 into 10 to the power minus 19. V minus nu minus nu naught. First let me obtain the nu minus nu naught here. Nu minus nu naught, that's going to be 8.2 minus 3.3 into 10 to the power 14 hertz. That's going to be equal to 4.9 into 10 to the power 14 hertz, right? Okay, so now you see, so what we're gonna have here, this is into 4.9 into 10 to the power 14, 4.9 into 10 to the power 14 volt. So now, okay, let me use calculator. So that's gonna be 2.03 volt. Okay, so this is the answer. This was asked in 2023 and 2020 also. This was repeated. Okay, so now let me show you the questions. Before I take the next question, let me show you the questions again. This one was asked in 2023, and this question was asked in 2024. Okay, and this one was asked in 2025, this one also 2025, this one also asked in 2025, right? So now let me take the next question. Sorry, here is the next question. Kinetic energy of an electron is 120 electron volt. Okay, so kinetic energy is 120 electron volt. Calculates its momentum and speed. Okay, we need to calculate the momentum and speed. We know that the relation between the momentum and kinetic energy is given by this relation, is given by root over 2m into kinetic energy, right? We know that. Okay, now you see mass of an electron. What is the mass of an electron? Mass of an electron is 1.9 into 9.1 into 9.1 into 10 to the power minus 31 kg, right? And here the kinetic energy is given in electron volt. Here the kinetic energy is given in electron volt, 120 electron volt. Let me convert it into joule. So that's going to be 120 into 1.6 into 10 to the power minus 19 joule, right? So that's why it's going to be 120 into 1.6 into 10 to the power minus 19, right? That's what we will get, right? So now what we can do here, okay, what do we need to find? We need to find momentum and speed. Okay, let's find the momentum first. So 2 into 120 is 3 into 2 square into 2 into 5. So this 2 and this 2 square, 2 square, 2 square, 2 to the power 4. So square root of 2 to the power 4 is 2 square, that means 4, right? That means 4. Then just give me a second. Okay, let me clean this. So within bracket we're gonna have 9.1 into 3 into 5 into 1.6, and if we make it 16, then we're gonna have, let me write this, 10 to the power minus 31, and if you make it 16, then here we're gonna have 10 to the power minus 20, right, instead of 10 to the power minus 19, right? So, and square root of 16 is also 4, so we can write here 4 4s are 16. So just give me a second. So here instead of 4 we're gonna get 16, right? Hope you have understood this. Now multiply this 3. So 3 1s are 3, 3 9s are 27, then multiply it by 5, 15, 1 carry. Then, okay, now let me use calculator to calculate this. Okay, I don't want to waste time. So here 16 into root over 136.5 into 10 to the power minus 51, and square root of this, let me do one more thing. Let me make it even. Okay, so in order to do that, what are we going to do? Okay, let me bring the decimal here so that it becomes 10 to the power minus 50, right? Hope you have understood this, right? So now you see here square root of this will be equal to 16 into 1.683 something. Okay, let me make it 1.1683 something. So let's keep it 1.17. let me take 1.17, and square root of this 10 to the power minus 50, that's going to be 10 to the power minus 25, right? So that's what we have got. Okay, so now let's calculate this again. Okay, now 1.17 into 1.6, that's gonna be equal to 18.72 approximately. Let me make write 18.7 into 10 to the power minus 25, right? This is the momentum, kg meter per second, right? So if we write this answer in standard form, if you bring the decimal here, then it's gonna be 1.87 into 10 to the power minus 24, 10 to the power minus 24. This is the momentum, right? So now let me find the speed. Okay, So now just let me rearrange these things. Okay, so here you see okay, speed. So we know that momentum is equal to m into v, right? So therefore v will be equal to p by m. So here we have got the momentum 1.87 into 10 to the power minus 24, and m, mass of electron, is 9.1 into 10 to the power minus 31 K. Okay, let me use calculator to calculate this. So it's gonna be approximately 2.05 into 10 to the power 6 meter per second. Okay, this is the speed, right? So now let me take the next question. This was asked in 2022. Okay, so now here you see this was asked in 2020. Let me answer this question. So here it is given, guess the shape of the curve which shows the variation of v naught with nu. Okay, now you see this equation is in this form: y is equal to mx plus c. Okay, so the shape of the curve of curve of v naught versus nu given by the equation v naught is equal to h by e into nu minus phi naught by e is a straight line, right? So it will be something like this. Let me show you here. So here you see, so this graph gonna be like this. So here this is the v naught and this axis will represent nu. Okay, and the graph will be like this. Okay, because here you see this part is if you compare this equation with y is equal to mx plus c, here y is nothing but v naught and x is nothing but here nu. Okay, and c is this minus phi naught by e. So that's why, so this axis will cut the this line will cut the y-axis. That means here v naught below the origin, because here we have minus sign. Okay, and this is nothing but phi naught by e, right? Phi naught by e. It will be negative below the origin. Okay, hope you have understood this. So now let me take the next question. This was also asked in AHSEC final 2020. So here, what did de-Broglie propose regarding wavelength lambda associated with a particle of mass m? So the wavelength proposed by de-Broglie regarding wavelength associated with a particle of mass m is given by lambda is equal to h by m into v if it is moving with velocity v, right? Okay, here let me write it properly. Okay, so according to de-Broglie, the wavelength of a particle of mass moving with velocity v, to represent velocity I am writing small v. When I will write capital V, this one in this way, that will represent potential. Okay, so velocity is lambda is equal to, sorry, mass, I haven't mentioned the mass is m here. Okay, that is given by Planck's constant h by m into V by m into V. Okay, H is Planck's constant. Right, so now here you see if an electron of mass small m is accelerated, sorry, let me write it properly, is accelerated from rest through a potential V. Let me write here capital V to represent potential. Okay, then the kinetic energy will be given by E into V. Kinetic energy gained by the electron will be given by E into V. Right, now you see, we know that momentum, which is equal to m into V, this m into small v is the momentum. Here is, we know, momentum is equal to 2 into mass into kinetic energy. Here the kinetic energy is nothing but 2 kinetic energy is E into V, this E into capital V. So now let me use equation number 2 in 1. This is equation number 2 and this is 1. Okay, then what we're gonna have, then we're gonna have lambda is equal to, so let me use another ink. Okay, so we're gonna use this equation number 2. Here you see value of m into V in equation number 1, right? So that's using 2 in 1, but so please do write the sentence. Okay, using 2 in 1. Okay, let me write here, using 2 in 1, we get that lambda is equal to h by root over 2me into V. That's what we get, right? So here h by this denominator can be written as 2 into m into E into root over V. We can write that way. Okay, now value of this part is given, that is equal to 1.227. so that's why it can be replaced by 1.227. then we're gonna have lambda is equal to 1.227 divided by root over V. Okay, divided by root over V. This is what we needed to show. Okay, hence proved. Hope you have understood this. Now let me take the next question. So here you see, this one was asked in 2023. So here you see lambda p is the wavelength of proton and lambda alpha is wavelength of alpha particle. So now alpha particle is heavier than proton. Alpha particle is heavier than, that means mass of alpha particle is greater than mass of proton. Okay, now we know that de-Broglie wavelength, according to de-Broglie wavelength, lambda of proton will be given by h by momentum of proton, that means mass of proton into velocity. Okay, similarly alpha particle wavelength of alpha particle will be given by Planck's constant, mass of alpha particle into velocity. So here you see, as the mass of alpha particle is greater than this, so its momentum will be greater. Momentum is greater means wavelength is shorter. So that's why correct option is this. So wavelength of alpha particle is shorter than proton, so wavelength of proton is longer than alpha. That means option 2 is correct. Hope you have understood. Now you see, this question was asked in 2022 AHS final under Assam Higher Secondary Education Council. So here we need to fill in the blanks. So according to de-Broglie, you know, natural law of symmetry, right? And so that particles and radiation must be symmetrical. Okay, so here you see particles and radiation must have symmetrical character. Okay, so this is what this is radiation. Okay, R A D I A T I O N. Okay, so thank you for watching. See you in the next video. Bye bye.